Today we shall study about application of Gauss law in electrostatics. Application is done in different material. The first is infinitely long straight uniform charged wire. Second is uniformly charged infinite plane sheet. And third is a spherical shell. Now the first, the field due to an infinitely long straight uniformly charged wire. The figure is shown in A and B. The A figure is the symmetry diagram and B figure is with the Gaussian surface. Now, we consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is obviously an axis of symmetry. Suppose we take the radial vector from 0 to P and rotate it around the wire. The points P, P dash, dash dash so obtained are completely equivalent with respect to the charged wire. This implies that the electric field must have the same magnitude at these points. The direction of electric field at every point must be radial. Outward if lambda is greater than 0. Inward if lambda is smaller than 0. कहने का मतलब है कि चार्ज डेंसिटी जब 0 से बड़ा होगा तो ये ई आउटवर्ड होगा और जब 0 से छोटा होगा तो इनवर्ड होगा. This is clear from figure 1. Consider a pair of the line elements P1 and P2 of the wire as shown. The electric fields produced by the two elements of the pair when summed give a resultant electric field which is radial. The components normal to the radial vector cancel. This is true for any such pair and hence the total field at any point is P is radial. Finally, since the wire is infinite, electric field does not depend on the position of P along the length of the wire. In short, the electric field is everywhere radial in the plane cutting the wire normally and its magnitude depends only on the radial distance r. To calculate the field, imagine a cylindrical Gaussian surface as shown in figure. Since the field is everywhere radial, flux through the two ends of the cylindrical Gaussian surface is 0. At the cylindrical part of the surface is normal to the surface at every point and its magnitude is constant. Since it depends only on r, the surface area of the curved part is 2 pi RL, where L is the length of the cylinder, flux through the Gaussian surface is equal to flux through the curved cylindrical part of the surface, बराबर E गुना 2 pi RL. The surface includes charge equal to lambda L. Gauss's law then gives E गुना 2 pi RL बराबर lambda L by epsilon naught. It means E बराबर lambda बटा 2 pi epsilon naught R. Vectorially, E at any point is given by E बराबर lambda बटा 2 pi epsilon naught R unit vector N, where N is the radial unit vector in the plane normal to the wire passing through the point is directed outward if lambda is positive and inward if lambda is negative. Second, field due to uniformly charged infinite plane sheet as shown in the figure. Let sigma be the uniform surface charge density of an infinite plane sheet. We take the x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates and its direction at every point must be parallel to the x direction. We can take the Gaussian surface to be a rectangular parallel pipe of cross-sectional area A has as shown. A cylindrical surface will also do as seen from the figure. Only the two faces 1 and 2 will contribute to the flux electric filled lines are parallel to the other faces and they therefore do not contribute to the total flux. The unit vector normal to the surface L is in x direction while the unit vector normal to the surface 2 is in the x direction. Therefore, flux E is as through. Both the surfaces are equal and add up. Therefore, the net flux through the Gaussian surface is 2EA. The charge enclosed by the closed surface is sigma A. Therefore, by Gauss law, 2EA बराबर sigma A बटा epsilon naught और E बराबर sigma बटा 2 epsilon naught. Vectorially E बराबर sigma बटा 2 epsilon naught unit vector n, wherein is the unit vector normal to the plane and going away from it. E is directed away from the plate if sigma is positive and forward to plate if sigma is negative. E is independent of x also. Field due to a uniformly charged thin spherical cell. Let sigma be the uniform surface charge density of a thin spherical cell of radius r. The field at any point P, outside or inside, can depend only on r. The radial distance from the center of the cell B to the point and must be radial. It means the radius vector. Field outside the cell. Consider a point P outside the cell with radius vector r. To calculate E at P, we take the Gaussian surface to be a sphere of radius and with center O passing through P. Thus, by Gauss law, E गुना 4 pi r square बराबर सिग्मा बटा epsilon naught 4 pi r square और सिग्मा बराबर और E बराबर सिग्मा r स्क्वायर बटा एप्सिलॉन नॉट r स्क्वायर और q बटा 4 पाई एप्सिलॉन नॉट r स्क्वायर वेक्टोरियल E बराबर q बटा 4 पाई एप्सिलॉन नॉट r स्क्वायर. E is outer barred if q is greater than 0 and barred if q is more than 0. Field inside the cell. If in figure B, P is inside the cell. The Gaussian surface is again a sphere through P centered at x. The flux through Gaussian surface is E गुना 4 pi r square. In the case of Gaussian surface encloses no charge, then by Gauss law E गुना 4 pi r square बराबर E बराबर 0 and r is smaller than r.